This is Art Thayer, Director of Energy Efficiency Programs with the Michigan Electric Cooperative Association, also the President of the Michigan Geothermal Energy Association. We'll be discussing two different types of heating and cooling systems today, that being a ground source heat pump, also known as geothermal heating and cooling, and an air source heat pump. Both of these have very high efficiency levels, but each of these deliver the heat in a different way. We'll discuss the advantages of each so that you will be better able to make a decision on which one fits your application the best. We will start with a short video on geothermal heating and cooling systems produced by the Geo Exchange organization in Washington, D.C.
Because the Earth absorbs and stores much of the energy it receives from the sun as heat, underground temperatures remain constant at a point between 42 and 80 degrees Fahrenheit year-round, depending on where you are in the United States. A geo-exchange system can use this energy source to economically heat and cool almost any kind of building, heat water, provide refrigeration, and perform many other kinds of applications. A geo-exchange system is made up of three components: a heat pump, usually located inside the building where it's protected from the environment and vandalism; an underground heat exchanger to act as a heat sink to store energy in the earth when cooling, and to extract energy from the earth when heating; and a distribution system, such as air ducts or hydronic radiant floor tubing, to provide comfort control for the building space. The two types of heat exchangers commonly used are open loop and closed loop. A closed loop system uses a system of continuous underground pipe loops in which both ends of the pipe system are connected to the heat pump, thereby forming a sealed closed loop. Water, or a mixture of water and environmentally friendly antifreeze, circulates through the loop to transfer heat between the heat pump and the earth. In some installations, the pipes of a closed loop system can be placed in a horizontal trench dug below the frost line. The number of pipes in each trench and the number of trenches needed will vary depending on the size of the geo-exchange system being installed and the type of soil found in the area. To minimize trenching, slinky coils, spring-like coils of polyethylene pipe, can often be used to increase the pipe surface area and thus the heat exchange per foot of trench. In locations where space is limited or a large heat exchanger is required, the pipes of a closed-loop geo-exchange system can be installed vertically in wells drilled into the earth. As with the horizontal and pond loop systems, the number of loops and the depth of the wells needed in a vertical closed-loop system are determined by the size of the building, system demands, the ground temperature, and other variables. Since it's not necessary for the heat exchanger to be connected to the rest of the system above ground, whichever type is installed can be placed within existing landscaping, under sidewalks, driveways, and parking lots, or even beneath the building itself. In an open-loop system, on the other hand, groundwater from an aquifer is pumped through one well and passes through the heat pump where heat is added to or extracted from it. The water is then discharged back to an aquifer or harnessed for other water management uses. Because the system's water supply and discharge are not connected underground, the loop is open.
Geothermal systems are really solar. The sun's energy is absorbed in the earth every single day. As a matter of fact, 50% of the sun's energy is absorbed in the earth every day. It is that energy that is in the earth below our feet that we are using to heat and cool your home. When you look at the geographic area of the United States, we can see in extreme northern climates, we have a constant earth temperature of 37 degrees. In southern climates, as high as 77 degrees. Now you look at the 37 degrees in extreme northern climates and you're saying, well, how in the world can we heat with only 37 degree ground temperature? I must remind you that there is heat in anything above absolute zero. Absolute zero is minus 460 degrees Fahrenheit. So anything above minus 460 degrees Fahrenheit, there is heat energy. So when you look at 37 degrees, that is far above the minus 460 degrees Fahrenheit. So we have plenty of heat to work with to move this heat into the structures that we need to do that. Basically, we use 1 unit of electricity, and that unit of electricity is through our pumps and our fans. And that extracts 3 units of geothermal energy out of the ground. It equates to 4 units of heat energy for every 1 unit of energy that's used to do that. That means it's 400% efficient. Today's technology actually gets into 600% efficiency. So imagine that. For 1 unit, you get 6 times the use out of that. When you look at a fossil fuel furnace, fossil fuels being propane, fuel oil, natural gas, wood, all of those things, because they combust, they burn, we have to have a venting system to get that pollution out of the house. All that carbon monoxide and other pollutants, we need to vent that out. That equates into less than 100% efficiency. Today we can get up to a 97 or a 98% efficient natural gas furnace. That is still less than 100%. We will never get to over 100% when we combust things. But when we're using the sun's energy and simply moving that, we have no combustion, we have no pollution, we have no carbon monoxide. So that's how we can get these efficiencies that are 5 to 6 to 7 times more efficient than a fossil fuel furnace. Geothermal energy, when you look at this little chunk of land, let's say you're on a small lot that has a road frontage of 40 feet, the lot depth is 100 feet, and then we go 150 feet down in the ground. That equates to 300,000 kilowatt hours of energy, or 120 kilowatt. When you look at your utility bill, when you look at your electric bill, you can see that your normal consumption on kilowatt hours is far, far less than what this is. So we have an enormous amount of energy beneath our feet every single day, and that's what we're tapping into. When we compare the efficiency levels, we can see on the far left of this graph, geothermal at 400%, and again now, today, much more than that, it's up to 600%. The air source heat pump around 200%, electric resistant at 100%. In every fossil fuel from there to the right of the graph, you can see is less than 100%. If you look at your typical home, residential energy use, about 64% of your heating and cooling costs are devoted to your energy bill. About another 22% to hot water, 11% to appliances, and only 3% to lighting. So you can see here, heating and cooling comprises more than half of our energy bill every single month for the year. When you compare that to geothermal, more than 50% of the energy is extracted from the earth, and that is free energy. So now you're left with your heating and air conditioning of 19%, hot water 16%, appliances 11%, 3% lighting. So you look at that we can cut your energy bills typically in half just by using a geothermal heating and cooling system. In the heating cycle, what we do is we use what's called a refrigerant. Why do we use a refrigerant? Well, what that is it's a highly unstable mass that we can compress. It gets super hot, we expand it, it gets cold. So depending on whether we compress it, we expand it, we can get heat to move. The second law of thermodynamics says that heat moves to where there is no heat. So if we get that heat differential, we can get heat to move the direction we need it to go. So in the heating cycle, what we do is we expose a really cold gas to the water loop, and we recirculate that cold gas through the ground, which absorbs the heat from the ground into that cold liquid. And then we move it into a compressor and we compress that to a hot gas. So the heat moves from the earth into this cold liquid to the compressor, where we compress it to a high temperature. We move that into an air coil. We blow the cooler air across that hot air coil, and then it moves into the building structure. So we're simply moving heat from the ground into the gas, compress that, move it into the air. So simply moving heat from one place into another place. In the cooling cycle, we reverse the process. We're actually taking the cold liquid, exposing that to the air coil, so that hot, moist air in the summertime, we're moving across a cold coil. We're taking the heat, putting it into that refrigerant. We compress that to a higher temperature, and we circulate that higher temperature around the cooler water, and that is absorbed then back into the earth. So simply stated, in the wintertime, we extract energy from the earth. In the summer, we put it back to the earth. So we're simply moving heat back and forth, back and forth. This is also renewable energy, because what we're doing is taking heat from the ground, but we're also putting it back into the ground during the other season. There's a lot of different ways we can do this. There's several different types of loops that we can put in the ground to get this accomplished. The most common is what's called the horizontal closed loop. This is a loop that's typically 150 feet long by 230 feet long. The trenches are typically 2 to 3 feet wide, 4 to 6 feet deep. Typically there's 600 feet of pipe in that trench, called a 4-pipe trench. Why only 6 feet deep? If we dig any deeper, the ground doesn't get any warmer. So we can dig a whole lot deeper and don't gain any benefits. All we do is increase the cost. So 4 to 6 feet deep, we've got all the energy we need. These trenches need to be 10 feet apart from each other. Why 10 feet? Well, if we get them any closer, these trenches start to argue with themselves. They're trying to take heat from each other. These trenches need to be 10 feet away from each building, well, septic tank, etc. And again, why 10 feet away from the building? Well, if we're going to take the heat out of the earth, put it into the house, we don't want that loop too close to the house to where we're actually just extracting it back to the loop. That decreases your energy efficiency. Each of these loops, designed 150 to 230 feet, 2 to 3 feet wide, 4 to 6 feet deep, produces about 12,000 BTUs of energy. This is what a horizontal loop installation looks like. It is going to mess up your yard. We are going to dig these trenches. It's going to be deep. We're moving a lot of soil. If you don't have the length or the width for a horizontal 4-pipe system, we can do what's called a Slinky Loop installation. And this is where we kind of coil this up. If you remember the Slinkies of the days where we played with that thing, it's the same thing, that we coil this thing over. But it takes more pipe to do that, because every time you can see this pipe overlaps each other, that's a loss of energy. So we put in more pipe in a shorter distance. But if you don't have that 150 to 230 feet in distance in your lot, we can shorten that up by doing this vertical Slinky Loop installation. In a large pit situation, we can do a horizontal pit or slinky installation, where we just dig a big pit, we put these slinkies in. Now, you can do a directional bore horizontal system where we actually drill under the ground. We don't use a backhoe. We actually push this pipe and pull this pipe through. Another way to do it is an open loop system. This is quite common anywhere where we have good water quality, and we are out in the country where we don't have city water, and you have an open loop system or a well. What we do is we need to have adequate supply of water. That typically means a 4 to a 6-inch well producing 15 to 30 gallons a minute. We have to have good water quality. If we have a lot of iron and other things, that's going to clog up our heat exchangers, that's going to increase our maintenance costs. That may well negate the energy savings that we have. So we want to have that good water quality. We want to have a place to discharge it. That means we need a pond, a ditch, a stream, or a dry well. And a dry well basically is if you're in a sandy soil condition, we can bury a perforated pipe and we can discharge into that perforated pipe, and that water actually finds its way right back down to that aquifer that we're pulling the water out from the well. And it actually ends up being almost a closed loop system because we're just discharging back to the ground, which seeps back down to the well, and we reuse that water over and over again. A typical open loop system looks like this. You've got your well driller coming in. You end up with this little standpipe here that's a code here in Michigan. We tap into then your existing water on the inside. We just tee off from the existing water. On the left-hand slide here, we can see in the upper right-hand corner there's a water line that kind of goes up out of view. That's the water that's actually coming over to the right-hand side of this slide, going down into this geothermal system. This system here is actually called a split system. If you've got a good heating and cooling system, or a good heating system, in this case it's a fuel oil furnace, we can add a split to it. We can save substantial amount of money by doing this on an open loop and a split system. You can see that orangish red line that moves off to the right hand side of the picture on the right picture. What that is doing, that is the refrigerant line that goes to an air coil over the fuel oil furnace. So this heats and cools, and then when the temperatures get so severe in the wintertime that this geothermal system, based on its sizing, can't keep up, then it fires off the fuel oil system for those very short periods of time. If you don't have the space for the horizontal closed loop system, let's say you don't have that 150 feet to 230 feet deep lot, we can do a vertical loop. Say you're in a subdivision. Vertical loops need to be about 150 to 250 feet deep. They're 10 feet apart from each other, 10 feet away again from the buildings, the wells, the septics, anything else, and each well produces the same amount of energy, about 12,000 BTUs or more. This configuration, if you think about it, if we're 10 feet apart, 150 feet long on a horizontal loop, that's 150 feet by 40 foot area that needs to be clear of no buildings, wells, septic tanks. If you don't have that, we can do the same thing in a 10 by 10 area, because now we're going straight down instead of horizontally. In fact, it doesn't even have to be a 10 by 10 area. It can just be 10 feet long that's 10 feet away from a building. So it doesn't have to be a square. It can be in a straight line. So you can see the opportunities here where we can get geothermal systems into a very, very limited amount of space. Now, a vertical closed loop system on a commercial job, we generally do a combination of this big, huge header pit, the well driller on the left. We can see the bore hole on the upper right. And then we can see the header pit where we're tying all of these holes together to bring in the amount of BTUs that we need for this large structure. When we look at a large commercial application, you can see internally we're bringing all of those loops into a single pumping structure. And on the right-hand side, you see a building that's in the wintertime. The southern part of that building is getting very warm with the solar absorption through the brick. But the office buildings on the northern side of that are getting very cold. So what happens with geothermal is we simply move heat to where there is no heat. So we're taking the heat from the southern part of these buildings, moving it to the northern part of the buildings. We haven't even tapped into that energy in the earth. We're simply just moving it from one place to another. If you think of a restaurant, we can take the heat from the kitchen area, move it out to the dining area in the winter times. So it's a very efficient way to utilize the earth's energy, the solar energy, or the ambient temperatures in the air to simply move heat to where it's needed from another place. We can also use a pond loop. Now, understandably, most people don't have a pond, but if you do, the minimum surface area needs to be a ½ acre. It can be no more than 100 to 150 feet away from the structure. Why is that? Well, if you remember in previous slides, a horizontal closed loop system trenches 100 to 150 feet long. So if we trench out to the pond, we may have enough trench to get the heating BTUs that we need. We don't need the pond. In the shallowest time of the year, we need that pond to be no less than 10 feet deep. So that's generally here in the Michigan area, the northern climates of around August or September. So if you've got a pond that's no less than 10 feet deep during August and September, no less than ½ acre in surface area, And no further away than 150 feet away from the building, we can use a pond. This actually saves in those trenching costs that we have in those multiple horizontal closed loop systems. So a lot of people say, well, what in the heck does a heat pump look like? What does a geothermal system look like? Typically, it looks just like your furnace. You've got your return air on the left, that silver duct on the left, that's return air coming into an air filter, going into the unit, which is either being heated and cooled, and it goes to your supply, which is at the top of that unit. The only difference is, instead of a gas line coming in or a fuel oil line coming in, you've got that flow center that's attached to the wall. That wall there has got this 1/5 horsepower pump that recirculates the water through that closed loop system in the ground, whether it's a vertical or a horizontal loop or a directional bore. And it's recirculating that water to either do the heating or the cooling. And the other neat feature of geothermal heating cooling systems is any excess heat that we have, we push it over into the water heater, and that is free hot water anytime that we have that excess capacity to do that. Some things to consider during your installation is the closed loop installation with a backhoe. It's going to disturb that ground, and it's going to take a year or so for that to settle back in. The vertical loops are more expensive because we have the well driller in there. The directional bore is even more expensive than the vertical loops. And of course the pond loops, you have to have that pond with all those criteria in place. The appraisal journal has found that there's more evidence of rational market values for home energy efficiency. They actually found that the home value increases by more than $20 for every $1 reduction in annual utility bills. What this means is once you've made this investment, not only did you realize all of the energy savings over the years that you've been in your home, but that the value of your home is much more when people are looking at your home for resale because of those low utility bills compared to other homes in the market. They also found that the home sells for asking price much more often with energy efficient homes, and they sell much quicker than those that aren't as efficient. So you have added benefits down the road. So we're going to move on into air source heat pumps. Now everything I said earlier about geothermal systems applies to air source heat pumps. We're moving heat to where there is no heat. We're using the refrigerant. We're compressing it either to a hot temperature or expanding it to a cold temperature to get the heat either to move from the outside to the inside or the inside to the outside. The only difference is that the unit sits outside, just like your air conditioner. We don't have that underground piping. So in those areas where you don't just have an opportunity to do the piping, or you don't have the finances to finance that additional cost for that loop that needs to be buried in the ground, the air source heat pump is a very, very good way to save on your heating and cooling cost. So it's a similar concept. It's a two-way air conditioner basically. It not only cools, but it heats. And it delivers up to 3 times as much heat as it consumes in energy. So again, much more efficient than a fossil fuel furnace that delivers less than 1 times of the fuel that it consumes. So it typically draws 1/2 to 1/3 of the electricity of a standard resistance heater, the same amount of heating reducing your energy bills. This typically compares to 70 to 95% of a fossil fuel powered boiler. Fewer moving parts, reducing maintenance requirements, but I have to remind you that anything that sits outdoors, like your air conditioner, typically is neglected. We need to make sure that those coils are cleaned. If we don't clean those, then our efficiency levels go down dramatically. So we don't have the typical combustion of fuel oil, propane, or natural gas, or wood. So we don't have the concerns of carbon monoxide or any of those pollutants in the house or outside of the house. An air source heat pump can also be used to heat your water as well as your air. And the same system may be used for air conditioning in the summer as well as heating in the winter. Lower running costs than other fossil fuel furnaces, as I mentioned before. Heat pumps lose their efficiency as external temperatures fall, particularly in the wintertime. And this is important. This is the difference between an air source heat pump and a ground source heat pump. The air source heat pump is limited to its ability of the outdoor air. The ground source heat pump can go year-round because it's in that constant ground temperature. So you have to be aware of your climate and your outdoor air temperatures, and at what point can you use a standalone air source heat pump. In North Carolina South is primarily the technology. Everybody's using an air source heat pump. The further north we get, particularly into the upper peninsula of Michigan, the ability for them to actually do all the heating in those severe climates diminishes greatly. So you have to be careful about where you're at in your climate to consider the air source heat pump. And that air source heat pump costs less for installation because we save on those loop costs. I do want to mention there's a lot of geothermal manufacturers out there, many of these listed on this page. It is important to note that you want to make your selection for a geothermal system based on the experience and the expertise and quality of a contractor, not the brand of the equipment. Good contractors will carry a good brand of equipment. But you can't turn that around. You can't say because they have a good brand of equipment, they're a good quality contractor. You can buy the best piece of equipment in the world, but if it's not installed right, it's not going to work right. So you have to make sure you get a good quality contractor. The best way to do that is to visit earthcomfort.com, www.earthcomfort.com. That is the website for the Michigan Geothermal Energy Association. There's a lot of good information out there. A lot of what we've talked about today is out there. And you can also find quality contractors in your area. I hope this was beneficial, and I wish you the best of luck in deciding on your next most efficient heating and cooling system. Thank you.